Okay, today we're going to look at independent and dependent events, but before we do, we'll make sure we understand the difference. So, in our last topic, we were doing probabilities that had to do with two things like mutually exclusive. We were looking at what's the chances of two things happen at the same time, or two different outcomes for one event. So, for example, the word things were worded like, what's the chances you would get a heart or clubs in the event that you did drawing cards. So in that case, our probability was A or B, so we used union, and basically it was we just add the two together. And then the only thing that was important was deciding whether if they were not mutually exclusive, then we had to subtract them. So for example, if we did hearts or clubs, you'd have 13 out of 52, and 13 out of 52, you'd add the two together, you get 26 out of 52. If we said what's the chances you got a heart or a 7, so we'd have 13 hearts, we got 4 sevens, but we had to subtract any overlap. So we'd subtract the ones that are hearts and sevens, which was 1 out of 52. So that was the only thing to be aware of with mutually exclusive. What we're moving on to today is a little bit different. We're looking at whether things are independent or dependent. And instead of it being one thing happening at a time, we look at two events. So I'm going to draw a heart, and then I'm going to take another card out of the deck and draw a heart again. So that's the difference. So two different events, one after the other, and the key thing that we're looking at is the word and. So in this case, for these events, we're looking at the intersection. We're looking at A and then B occurring. All right? Okay, so when we're looking at independent and dependent, what we're doing is we're looking at two different events, and the idea is, are they related to one another? Does the second event change because of what happened in the first? So for an independent event, if we're dealing with cards or taking something out of a bag or something, it depends on whether we put that thing back or not before we draw the second card. If it's things like a dice, obviously we roll one dice, you roll the next dice, the results of the first one doesn't affect the second roll. If you were doing a spinner and a dice, that type of thing. So independent events, we're looking at what happens when we have A and B together, and when there's both of them, we basically, because it's and, we multiply. So we multiply the two probabilities together. So for this example, an example would be, let's suppose we do probability of getting two hearts. So to get two hearts, you'd have 13 out of 52, and we're going to put that card back in the deck. We're going to replace that card. Then the second heart would be 13 out of 52 again. Okay? So if there's a replacement, it's pretty straightforward. If, let's do another one. Let's suppose we roll one dice, and we want to know what's the chances of getting a 6. So you'd have 1 out of 6 chances to roll a 6. Then we're going to roll another dice. What's the chances we get another 6? You'd have 1 out of 6, and so on. Okay? If I said what's the chances we get a 6, and then we would get an even card, or an even dice, so then we would just change that to 3. If the first one is a 6, the second one, 3 out of the 6 are even. So it's pretty basic when you're doing the word and. Just make sure you multiply the two. When we do dependent events, what happens now is the second probability changes because the numbers get reduced after we do the first one. So for example, let's write the formula first. So you'd have A times B, and the only thing that differs is we write it as B/A. So that means the probability of A times the probability of B, given that A has already occurred. So this would be things like, what's the probability I get a clubs out of the deck, and then I'm going to take a second card without putting the first one back and getting clubs again. So clubs would be 13 out of 52. Then the second club, there'd only be 12 left, and there would only be 51 cards left. So when it's dependent, that second probability gets altered because of what happened in the first draw. Okay, so let's do another one. Let's suppose we had, what's the probability of getting 2 red cards in a row. So the first red card, you'd have half the deck, 26 out of 52, and then the second red card, you'd have 25 out of 51. Okay, let's do one more. What's the probability of getting a king and then a 5? So we want a king and then a 5. So the probability of a king, there's 4 kings in the deck out of 52, and the 5 would be, it's only 3 left over, so we'd have 3 out of 51. Sorry, I messed up on that one. There'd be still 4 5s left over because the king wouldn't affect it, so you'd have 4 out of 51. Okay, what would it be if I said, what's the chances you got a king or a 5 in any order? So because it's any order, we can kind of think of it like we did the last unit. Right? We could do the king and the 5, or we could do the 5 and the king, so we'd have to times it by 2 or 2 factorial. Or the other way of thinking about it is you'd have a king and a 5, and then a king and 5 again. So you'd have king and 5, or a 5 and then a king if you do the other order. So then you'd have exactly what we just had. You'd have 4 out of 52 times 4 out of 51 plus 4 out of 52 times 4 to 51. So you can see you just get the exact same answer twice. One thing to be careful of that some people mix up is they think these two things are the same, mutually exclusive and independent. They are not the same, because mutually exclusive means can these two things happen at the same time, and independent is can one thing happening affect the next thing that happens. So they're totally different, but they do work together because you can use the formulas together. So for example, for mutually exclusive, we know that A or B equals A plus B minus A and B, right, if there's overlap. So that's when it's not mutually exclusive, we use that formula. And for independent, we have A and B equals A times B if it's independent, or B slash A if it's dependent. So it doesn't matter, but you can see these two formulas are totally different, but they do overlap because this overlap and this can be used exactly the same. So when you get questions where they give you the probabilities, you might have to use the formulas to help you figure them out. So let's do one quick example. So the first one, it's saying if probability of A equals 1/3, probability of B equals 2/5, and A or B equals 3/5, the question is, are they mutually exclusive? So first off, mutually exclusive has no overlap, but because this one does have an overlap, so we'd say they're not mutually exclusive. So they're not mutually exclusive, so no. And the question is, are they independent? Well, if they're independent, then this second formula has to be true. So we can just plug the numbers in. So is 3/5 equal to 1/3 times 2/5? So if you multiply those out, that would be 2/15. And the answer is no, right? 3/5 is not 2/15. So because they're different, then we know that A and B, oh sorry, I messed this up, ignore that. Let's go back to the first formula, right? We're looking for, if they're independent, we know the second part is true. So what we have to do is we have to figure out what that equals. We want to figure out what that A and B is. So we know that 3/5 equals 1/3 plus 2/5 plus or minus the overlap. So 1/3 plus 2/5 is, if you do that on your calculator, that would be 6/15 and 5/15, so it'd be 11/15. So I can't do this in my head, I'm going to use my calculator here. So what we want to do is we want to figure out what is A and B. So on your calculator, if you go 1/3 plus 2/5, that equals 0.733, and we want to go 3/5 or that minus 3/5, so minus 3/5 equals 0.133, which as a fraction is, let me just try it differently here. Okay, so if we go 1/3 plus 2/5, we subtract 3/5, that equals 2/15. Okay, so that equals 2/15, so that means we know that A and B equals 2/15. Let me erase this off. So if we know that that part is 2/15, then the question is it independent or not? So then we would plug it into the formula. So that means we'd have 2/15 would have to equal 1/3 times 2/5, and if we multiply those, that is actually 2/15. So because both fractions are the same, then we'd say yes, they are independent. So this question wasn't mutually exclusive, but was independent. So any of these ones that you get like that, just use the formulas, plug in the numbers, and solve in that fashion. One other type of question you want to be aware of is if they talk about complements. So let's suppose the chance of passing math is 70% or 0.7, and then you would have a 30% chance to fail, obviously. And then let's suppose English, you have a 90% chance of passing, so that means you'd have a 10% chance of failing. So now the question would be, what's the probability that you pass both? So we pass math and English. So then you just make sure you pick the right probability. Chance of passing math is 0.9, English would be 0.7, multiply the two together, gives you 0.63. Okay, so then if the question said what's the chance of passing math but failing English, so then we want to do the complement. So math is 0.7, failing English would be 0.1, so we'd have 0.07 chance of doing that combination. Or if I said what's the chances we fail math but pass English, so then you'd have 0.3 times 0.9, which would be 0.27. And the last one, what's the chance, what's the chance we fail both? So math and English failed would be 0.3 times 0.1, which would be 0.03 chances of failing both. So you get the idea that you can multiply each of these either way. If the question was what's the chances you pass one or the other, then you would add all these together. So you would, if you pass one or the other or both, you would basically have all of these together. So all of those together would add up to 0.97. So you'd have a 97% chance of passing math or English or both, and then the 3% chance of failing both, which makes sense because those two have to add up to 100% as well. And that's it.